So in the practical on Friday, what we were looking at was this reaction. So we were looking at glucose going through various processes to give pyruvate, which then goes to acetaldehyde with release of 1 carbon dioxide, and that's what we were looking at in the syringes. And then we were looking at the action of alcohol dehydrogenase to give ethanol. And so this gives us NADH to NAD+. So this is our fermentation reaction. And then what we were doing in section 3, which is what I'm going to talk about here, is we added lots of alcohol dehydrogenase, and we made conditions to drive the reaction backwards, such that every ethanol should yield 1 NADH. And we can measure the NADH using the spec at 300 and whatever it was nanometers. So I'm just going to go through some of the sums from that here. So first of all, in section 3.1, we were thinking about about predicting the amount of ethanol and therefore NADH. So remember, this is a stoichiometric reaction. We'd get from a given amount, from a known amount of ethanol. And the first thing we have to deal with is a volume per volume concentration. So the ethanol we added, so this is part 1. That is messy. Let's try again. So in part 1, we know that the ethanol we added was at 0.0125%. This is volume per volume. So we know that 1% volume per volume means 1 mil in 100 mils. So 1 mil of pure ethanol in 100 mils. But here we've got 0.0125, so that's 0.0125 mils in every 100 mils. And let's work out the amount of pure ethanol per mil. That we added. So we just divide that by 100. So there we got 0.000125 mils in every 1 milliliter of the ethanol solution we added. Now in the second part, our goal was to work out the grams of ethanol added, not the mils. And to do that we use the density of ethanol. Which the red folder tells you is 0.79 grams per milliliter, so it's less dense than water is. So 1 milliliter volume of ethanol weighs 0.79 grams. So let's work out the grams per mil of our starting solution. So this is 8,000 times less. 0.000125 is 8,000 times smaller volume than 1 mil, so it would be 8,000 smaller number of grams. 8,000. So if we divide that by 8,000, we get 9.875 times 10 to the minus 5 grams. So this is the grams per mil of our starting solution. So we know that our ethanol starting solution is 9.875 times 10 to the minus 5 grams per mil. But we added 100 microliters. We added 100 microlitres, not 1 mil. This is the volume we added into our assay. So that's 10 times smaller. So the number of grams would also be 10 times smaller. So that's 9.875 times 10 to the minus 6 grams in 100 microlitres. Okay. The third thing we need to do is now we need to start thinking about the concentration in our actual assay tube rather than the concentration in our starting solution. So we had 100 microlitres, which contained this number of grams, and we added that into a 2.1 mil reaction volume. So now let's work out the ethanol concentration in grams per mil in the assay tube rather than the starting solution. So now we've got that number of grams, so 9.875 times 10 to the minus 6 grams in 2.1 mils, and let's go, forgive me, in grams per litre. So there'll be about 500 times more grams in a litre, in fact 476.2 times bigger volume, so there'll be 476.2 times more grams as well. So that would give us 0.0047 grams per litre in the cuvette. Good. Our next task is to work out the molar concentration. What's the molar concentration in the cuvette? For that we need the molecular weight of ethanol, which is 46.1. So 46.1 grams of ethanol in 1 litre gives us 1 molar. So that's our starting sentence, but we don't have 46.1 grams, we've got 0.0047 grams. So if we had that amount of grams in 1 litre, that would give, what did it give? 0.000102 molar, or 0.102 millimolar concentration. So there we go, that is the millimolar concentration in our cuvette. So now we need to use our equation. So we need to go from millimolar concentration to the expected absorbance, the predicted absorbance, and we know that the absorbance is equal to the extinction coefficient times the concentration times the path length, and we know that the extinction coefficient is 6.22 per millimolar per centimetre, and the concentration we also know is 0.102 millimolar, and the path length is 1 centimetre. And look, we can cancel out these units here, centimetres and millimolars, which is good because absorbance doesn't usually have units. So then we just need to multiply 6.22 times 0.102, and that gives us 0.63. And there's no units for absorbance, so that is the expected absorbance you would get if everything worked perfectly. So you've probably got something a bit lower than that. Right, Now let's go on to 3.2. So I'm just going to work through some model data here. So section 3.2, going the other way round. So here we had an ethanol sample of unknown concentration, and you found what the OD was after your reaction. Then you had to work out what the concentration of ethanol was in your tube. So let's imagine, this is the same example I put in the notes in the answer sheet on mole, that imagine that with a 10 times dilution gave you an absorbance at 300 and whatever it was of 1.12. This is pretty close to the perfect answer that we'd expect, because I do know the concentration of the ethanol you got. So this is about what you'd expect. So the first thing you need to do is to take into account the dilution of your ethanol. So if you hadn't diluted it, you would have got a 10 times higher absorbance, but you wouldn't because the machine wouldn't have been able to read it, but theoretically you would have. So using the dilution factor, so 1.12 times 10 gives you 11.2 change in OD. And then we're going to use this same equation, so the absorbance is single temperature times concentration times path length. So here we know the absorbance, we want to know the concentration, so that's 11.2, 6.22 per millimolar per centimetre, times the concentration times 1 centimetre. So these cancel out. We're going to end up, we've got some millimolar units here. So now 11.2 over 6.22. Then the millimolar kind of comes up to the top. So that's nice. So that's what our concentration is. And then that would be 1.8 millimolar is the concentration in the cuvette that we were actually reading. But then we need to take into account the dilution from the original solution going into the reaction. So that is 100 microliters volume going into 2.1 mils volume. And so we need to multiply by times 21. 0.1 mil to 2.1 mil times 21. So 1.8 millimolar times 21, that'll give us 37.8 millimolar, and this is the kind of number we'd expect you to be coming up with from your results.